Developing applications for computers is exciting, challenging and rewarding. It's a great way of training the most important part of your body, your brain, and keeping it fit over a lifetime. And it's an in-demand job both now and for the foreseeable future. But often I've wondered how our nascent developers know what's important and what's not as they start out on their journey. So what better way to do this than to look at what's taught to our young people and compare that with my experiences in a 35-year career in software development from the times of early PCs to now. What's taught is defined by the computer science curriculum and further refined by the various examination boards in their specifications for the subject. So my starting point is to map out the curriculum in detail and then ask myself, how much have I actually needed that knowledge in practice? To my surprise, there are things in the curriculum that I've never needed in my career, and others that I use all the time. You can then either agree or disagree based on your own experiences. All points of view are valid, of course, but these are mine. Okay, here's a whistle-stop story of my career to date. I'll show you a journey from my first job to today and split it into roles I've had, types of applications I've helped develop, technologies I've used in anger, and general skills I've developed along the way. I'll only mention those things in which I've developed a good level of skill, but of course there are many other things that I've encountered during that time. Hopefully it'll all make sense, so here we go. Even as a teenager, I'd always had an interest in computers and learned how to hack around with early systems such as the Microtan 65 and ZX80, learning some assembly language and BASIC along the way. My first job in software was as a developer working on embedded systems in motion control applications. These systems were sold as complete products to industry, and we wrote and used a bespoke operating system, implemented applications in assembly language, and unit tested as we went. On the desktop, we developed early Windows 3 applications in C, and I introduced structured development methods into our process, Jordan and Ward-Meller, to help us communicate ideas. The web didn't exist in those days, so you gained knowledge by reading books, reverse engineering other people's code, and by good old problem solving and experimentation. Those were the days. Next, I moved into the field of industrial automation, specifically in the oil sector. Again, it was a mixture of embedded systems, but now with both desktop and server-based applications. Windows was moving on to Windows NT, and we progressed to using a variety of real-time operating systems for the embedded side and OS 9 for control servers. A lot of the embedded stuff was used in safety-critical systems, but was still written in various flavours of assembly in C. I was a senior developer by then, but also had project management responsibilities for the development of our products. Due to their nature, visible and verifiable quality was a big issue. Testing, configuration management and release practices became important, as you might expect, and we needed a formal development process as well, which was built around the latest object-oriented ideas. The web still didn't exist in a useful form, so we analysed things and designed solutions by collaboration with our peers, reading books and articles and using plain old inspiration. I then moved on to another software company which provided products and projects across a number of industry sectors. My role was now a fully fledged systems architect and program manager working in pharmaceutical automation. I was still hands-on though. Things were very much project-based, so requirements management and business analysis were important skills to have. Our deployment operating systems were Linux and Windows using Corba and DCOM services, together with relational databases. They were classical distributed client-server applications, and we used C++ and SQL as our development languages, and even a smattering of Visual Basic. Later on we moved to Java, which was just beginning to appear on the scene. Well, time moved on and so did I. I was now working for a start-up software development company providing products to the healthcare sector. I had roles as a project manager, technical manager and general manager. I was still hands-on and even carried out the admin for our Linux network. By now, the web was very much in full flow, and our products reflected that. We used Java Enterprise Edition technologies like App Server, Directory Messaging and Enterprise Service Bus for our enterprise service products, and .NET for our desktop products, and latterly Android for mobile. We worked according to agile principles with a focus on testing throughout our processes. Delivering the high-priority, technically complex features first meant we could actively manage the risks inherent in any new development, whilst at the same time delivering value to our customer. After a successful career, I semi-retired early and became self-employed. hands-on once again and never too old to learn new things. I've developed full-stack websites and applications using Drupal, Django and Vue.js, learning PHP and Python along the way. I've created mobile applications in the fields of AR and computer vision using my old friends Java and C++. And in my spare time I like nothing better than a bit of hacking, reverse engineering and anything security related. You never ever stop being a software developer. Well, here's my career mapped out in a nutshell. As you might expect, over a 35-year career, I've had many roles, used many technologies and acquired a few skills along the way. So let's take a look at what our young developers of the future are learning right now. I'm mapping out the curriculum for the Computer Science GCSE. It's a summary of those published by the 3 main examination boards in the UK and what the majority of 16-year-olds work towards. The curriculum is broadly split into 2 parts: computational thinking and programming and computer science concepts. Both are of equal importance as far as the exam boards are concerned. I'm going to score each topic in the curriculum from 1 to 5, 1 meaning that I've hardly ever needed to know it, and 5 meaning that I use it all the time. I'll also take into account whether I think someone just starting out in development needs to know about that topic. Let's examine the computer science concepts. The first topic is about how data is represented. It includes number bases such as decimal, binary, hex, units, bits and bytes and so on, binary arithmetic and how characters are encoded. It also covers how images are represented, how sound is represented and data compression. I've certainly needed to know about number bases and units and sometimes character encoding. Hex and binary arithmetic were essential in my work on embedded systems, but not so much elsewhere. And character encoding is something that crops up now and again. So let's score them 4, 4, 3 and 2 respectively. As far as need to know how images are represented, and of course I do know, but I very rarely had to calculate sizes of images or care about the effects of colour depth and resolution. Similarly with representing sound, yes I know the concepts, but I've never needed to care about the effect of sampling rate and bit depth on file size or playback quality, so for me I'll score both of these a 1. Finally, for this topic, there's the concepts around the compression of data. It includes lossy and lossless and why compression is needed. Some boards require knowledge about how Huffman coding and run length encoding works in practice and to be able to interpret trees and do calculations. Personally, I've never needed to know anything about compression algorithms to that level of detail and would just look it up if I did need to know. So it's definitely a 1 from me. Okay, next comes the theory behind computer systems. It's grouped into the topics of computer systems architecture, hardware, in particular Boolean logic and circuits, and types of software. Most of these things are knowing things. You need to know of them, but rarely need to apply that knowledge. Let me explain. Let's take the first item in the systems architecture topic, that a computer has inputs, processes stuff, and has an output. Fine, but that's all you need to know. Knowing what a CPU, storage and I/O devices do is certainly necessary for working on embedded systems, but knowing how clock speed, cores and cache affects performance is probably not. Equally, knowing about the von Neumann architecture and the fetch-execute cycle in detail isn't really useful. Knowing that there's different types of memory used in a computer and different types of external storage is fine, but that's as far as it goes. So I'll award a generous 2. The next subtopic is hardware, which focuses mainly on Boolean logic and logic circuits. Now I've needed to know quite a bit about programming low-level devices, and as a hobbyist I've dabbled in electronics for many years, but I've never needed to design basic logic circuits or apply Boolean identities as a software developer. So for that reason the whole of the hardware topic gets 1. Finally, for this topic we have the role of software in computer systems. It covers understanding what system software, application software and utility software are, and the concept of programming languages in general. They represent a body of knowledge that everyone in development would need to understand. I'll score it a 3, but only because it's something that students are required to know rather than something they use. For instance, you don't need to know that Python is a high-level language in order to use it. The next topic is that of computer networks, covering what they are, a logical view of them, how they work, and a physical view. All very important. But as a developer, do you really need to know this? The first subtopic covers the concept of a network and its advantages and disadvantages. The concept is fine, but I've never needed to know about the risks and benefits, so I'll score a 2. Then comes the logical view of networks. It covers what networks are, types such as LAN and WAN, the internet as a network, topologies, and the roles of devices on a network. Certainly as a systems administrator, network administrator, I did need to know a lot about networks, but as a developer not so. And certainly not about the advantages of star, bus or mesh topologies. So the logical view of networks gets a 2. How networks work, addressing in protocols, is something that is useful during low-level hacking all the way up to service-level programming. However, knowing the details of a 4-level TCP/IP model isn't something that concerns most developers. I'll score this subtopic 3. Finally, we have the topic of the physical view of networks, wired and wireless, materials, calculating performance, and knowing about various devices such as routers and switches are the subject areas. Interesting if you're a network administrator, but academic for developers, and it's covered in such a superficial way in the curriculum that I can only score 1. Security of computer systems, attack methods, defense methods, and pen testing form the next topic. There's a lot covered, from looking in detail at things like SQL injection, when most students probably have never used SQL in anger, to pen testing, when testing in general is hardly covered in the curriculum. For defense methods, ideas such as encryption, firewalls and MAC filtering are included, probably just words to most students. Sure, security is super important in modern systems development, but from my experience most developers know very little about it and rely on the frameworks and libraries they use to deal with it. It's a specialised field requiring special skills. So for instance, I only started doing any serious pen testing when developing a relatively complex website. So my issue with this part of the curriculum isn't so much that it's included, more so that the content is not aligned to the level of other knowledge someone will have at this stage. So for that reason, I'll score each of these topics a 3. The final topic on the concepts part of the curriculum is impact on society, which covers ethical, legal, cultural and environmental aspects of digital technology. I guess you consider a lot of these during development, but just as decision points. For instance, is it ethical to allow users to make comments freely on a website without moderation? And what are the legal implications of doing so, and so on? Most of these types of decisions are made when discussing requirements, usually by experienced people, as it's such a minefield. I have needed to make these decisions, but not until late in my career, so for that reason I'll score this whole section a 1, as it's not really relevant to this age of student. Okay, so that's the computer concepts part of the curriculum covered. Let's now turn to the topic of computational thinking and programming. This part of the curriculum is divided into 2 parts, algorithms and programming. Algorithms cover what they are and how to create them. Programming covers what you might expect, albeit in a procedural and functional perspective, but more on this later. Let's look at the part of the curriculum dealing with algorithms, what they are, how they're represented, pseudocode or flowchart. Some examples and how to choose the best one are the main ideas here. Problem solving in terms of abstraction and decomposition are also included, but superficially so. Creating algorithms is essential in development, as you won't have code without them. The curriculum suggests documenting them by pseudocode or flowcharts. However, algorithms are usually created by developers using a mixture of code, natural language such as English, diagrams, mathematical notation and such like. They find a way of sketching out their ideas that's natural to them. In the early days of my career, I saw junior developers using flowcharts to describe an algorithm, but not since. I've never really seen real-life software expressed in pseudocode, although it is more commonly found in academic papers. Equally, the curriculum suggests using trace tables as a way of understanding algorithms. Again, I've never seen anyone do this in real life for anything remotely complex. Instead, they reverse engineer the algorithm into a form they can understand, such as English or sketches. So I'll score the representation of algorithms 3, as it's absolutely necessary, but not in the way suggested in the curriculum. Next come some examples of algorithms, those old favourites of searching and sorting. For some reason, students are expected to understand and explain how linear and binary search works, as well as various sorting algorithms. More often than not, a programming language either provides default methods of searching and sorting, or you use a specific library to do so. And as you might expect, I've never needed to know how these standard methods work under the hood, and they're definitely not the same ones as on the curriculum, so I'll score each of these 1. Choosing algorithms based on performance and data requirements is something you do infrequently and is really part of system optimization, so I'll score this 2. Finally, for the algorithms topic comes the principles of problem solving, abstraction, decomposition and algorithmic thinking. This is a massive part of software development, so I score at 5. Sadly, this forms a very minor part of the curriculum, which is completely out of step with how systems are developed in practice. If there's one thing that makes a difference between an average developer and a great one, it's their ability to understand and solve problems. The final topic of the computer science curriculum that I'm going to look at is programming. Needless to say, this is the most important part of software development, and I'm going to give the whole of this topic a score of 5, but with some exceptions that I'll get to. First, let's quickly break down the programming curriculum. Whilst there are many gaps in the content that you would need to write a serious program, it does form a solid basis for a beginner. First, the building blocks of programming to put in place: data types, variables, constants, assignment, identifiers, sequence selection and iteration, and then the concept of subroutines. Next are the operators: Boolean, relational and arithmetic, followed by data structures, I/O and string operations, all still worthy of a score of 5. We then have the equally important details of procedures and functions. The curriculum very much takes a procedural view of programming rather than, say, object-oriented view. Nevertheless, the general need for these, the ideas of parameters, returns and local variables, are covered as you would expect. Again, score of 5. Then there's random number generation. I've used this when writing simulations, but rarely, so I'll give this topic a score of 2. Another non-5 score, I've given it a score of 3, are relational databases. I've used and written SQL for many databases such as Oracle, SQL Server, MySQL and so on, but nowadays developers typically use ORMs or higher level classes for accessing databases. In any case, developers usually write really bad SQL. Nevertheless, knowledge of SQL for students isn't a bad thing, but will prove difficult for them without some form of understanding of data modeling. Robust and secure programming is the next topic. It covers simple data validation, very basic user authentication, simple testing, identifying errors in algorithms and code, and categorization of errors. In many large projects I've been involved with, testing has accounted for almost as much effort as implementation, so this topic is definitely scored 5. Sadly, it's poorly covered in the curriculum for some reason. The last topic in the programming section is a small one, the concept of an IDE. Needless to say, this scores a 5, and even if they don't use a single IDE, every developer will organise a set of development tools for themselves to suit their own way of working. Well, that's the curriculum mapped out. Let's apply the scores I've awarded and see what we're left with. There you go. My view of what in the GCSE Computer Science curriculum is important to learn and what's not so. Remember that the exam boards weight programming and the theory of computers equally, whereas for me it's about 90-10. I've spent massively more time problem solving in programming as opposed to using my knowledge about the theory of computer systems. Of course, to pass exams you need to know everything on the curriculum, but once you've done that, focus on the important stuff and your first steps towards a career in software development will be a whole lot easier. Well, I hope you've enjoyed this video, so do subscribe if you'd like to know more.